Hello guys, so looking at parallel capacitors, parallel connection of capacitors. This is the symbol for capacitors. The two lines are equal, while this other one where one line is higher than the other is for potential difference. So this is the connection of parallel capacitors. For parallel capacitors, there is a break in the wires in the connection. This is the first capacitor, capacitor 1. Before it gets to 2, there's a break in the line. You can see that there's a break in this line before it gets to 2, before it gets to 3. So that is what you use to differentiate parallel capacitor and series capacitor. For series, there's no break in the line. So note that for parallel capacitor, there's a break in the line in the wires. So for you to be able to solve questions involving parallel capacitors, you need to know certain rules. The first one is the equivalent or combined capacitance is given as C equals to C1 plus C2 plus C3. In this connection, the equivalent capacitor is equal to C1 plus C2 plus C3 when you're talking about parallel connection. This is how you get it. Let's say for instance you have 1 farad, we have 2 farad, you have 3 farad. The total capacitance will now give you C equal to 1 plus 2 plus 3, which will give you 6. That is for parallel connection. So you have to note this for parallel connection. The equivalent capacitance is given as C equals to 1 plus 2 plus 3. You add it directly. Now, the second rule you need to know is C1, C2, C3 are all at the same potential difference. This is not the case for series connection. For parallel connection, they are all at the same potential difference. This capacitor, this one, they are all at the same potential difference. Do not forget this. Now, for parallel connection, each of the capacitors have its own charge. Each of the capacitor has its own charge. So C1 has Q1 to be its charge, C2 has Q2, C3 has Q3 to be its charge. So each capacitor has its own charge. The charge flowing through each capacitor is different for each capacitor for parallel connection. So the total circuit charge Q is equal to Q1 plus Q2 plus Q3. So where Q1 is equal to what? C1V, Q is equal to C2V. You know the reason why V is the same is because it's the same potential difference. They are all at the same potential difference. That's why V is the same, even though you have Q1, C1, Q2, C2. So note these principles. Now let's solve this question. What is the equivalent capacitance of a 3 microfarad capacitor and a 6 microfarad capacitor connected in parallel? But before we delve into this, I want you to take note of this. We have millifarad, that is 10 minus 3 farad, microfarad, 10 minus 6 farad. Please take note of the symbols. Nanofarad, 10 to the power minus 9 farad, picofarad, 10 to the power minus 12 farad. So now, this is the question. What's the equivalent capacitance of a 3 microfarad and a 6 microfarad capacitor connected in parallel? Now, there are 3 things to take note of. They're asking to what is being asked of you. You're being asked to get the equivalent capacitance. That's number 1. Then equivalent capacitance of what? Of a 3 microfarad capacitor and a 6 microfarad capacitor connected in what? Parallel. Now, this is what you use to get your answer. Now, since it's parallel connection and since that's asking us for equivalent capacitance, the formula is C equals to C1 plus C2 plus C3, depending on the number of capacitors that we are given. So they give us just 2, this and this. So our answer will be C equals to 3 microfarad plus 6 microfarad. That will give us 9 microfarad. In some cases, you'll be asked to convert this to farad. Since microfarad is 9 times 10 to the minus 6, this will be your answer. So this is how it works for parallel capacitor. You just add directly when you're asked to get the equivalent capacitance. So this is our next question. Most capacitors question normally come in this diagrammatic form, where you'll be given different capacitors arranged in series and parallel connection, and you'll be asked to solve for them. Now let's go straight to this question. The diagram above shows two capacitors P and Q of capacitance 5 microfarad and 10 microfarad. The charges stored in P and Q respectively. Sorry, find the charges stored in P and Q respectively. Now they're not asking us to get the equivalent capacitance, they're asking us to get the charges stored in P and Q respectively. Now what we are being asked to get is, what is the charge flowing through this 5 microfarad capacitor and the charge flowing through this 10 microfarad capacitor? Now I gave a formula, don't forget this, that Q, let's call this Q1 and let's call this Q2. For a parallel connection, for you to get Q1, that is the charge flowing through a specific capacitor, Q1 is equal to C1 times V, and Q2, depending on the question, is equal to C2 times V. Now the potential difference, since its parallel connection, is the same for all capacitors, but the charge is different and the capacitance is also different. So let's get the charge for our C1, that is 5 microfarad capacitor. This is C1, this is C2. So Q1 give us, our C1 is what, 5 microfarad, and our potential difference V, you can see it from here, is 20 volts. So 5 times 20, that will give you what, 100 coulomb. The reason why it's coulomb, because charge, the SI in for charge is coulomb. So our C1 capacitance, our 5 microfarad capacitor rather, has 100 coulomb. So let's get for Q2, which is C2V. The V is the same because for parallel connection, the potential difference is the same for all capacitors connected. So our Q2, our C2 is what, 10 microfarad times our potential difference is 20 volts. So 10 microfarad times 20, that give you 200 coulomb. Take note is 100 microcoulomb and 200 microcoulomb. The reason being that we did not convert the microfarad to farad. We just solve directly. In certain cases, they will ask you to convert to farad, and when you do that for this, it will give you, this microfarad stands for 10 to the power minus 6. That will give you 100 times 10 to the power minus 6. When set to standard form, will give you 1.0 times 10 to the power minus 4 coulomb. This is not supposed to be here. So this is 200 times 10 to the minus 6 coulomb. I'll give you 2.0 times 10 to the minus 4 coulomb. So this is the answer for this question.